Hello! This video is a brief summary of our work, Unsupervised Entity Alignment for Temporal Knowledge Graphs. Hope you'll enjoy it. As we know, knowledge graphs are very useful and can facilitate many applications. A knowledge graph is a set of triples with entities at the head and tail and a relation in the middle. However, knowledge graphs are highly incomplete, and the task of entity alignment is to find the entities that refer to the same real-world object. Here is a figure of a temporal knowledge graph. The temporal knowledge graph attaches timestamps on triples, so, compared to the normal knowledge graph, the temporal knowledge graph has richer information. As shown in this figure, we cannot distinguish these nodes with only relation information, but we can know that these two entities are different using temporal information. Previous works do not fully exploit the temporal information. They simply add an additional embedding layer in the graph neural network to represent timestamps. They don't work well because they get stuck on the objective that is designed to focus on training labels. To improve the performance, we try to encode the relational feature and the temporal feature separately. Here is an overview of our method. We separate the time feature encoder from the graph neural network. We use two different encoders, namely temporal encoder and relational encoder, to capture different features. When we don't have any pre-aligned pairs, the pairs found by the temporal encoder can serve as training data. The decoder takes the output embeddings of the encoder and fuses them together to get the final result. For the encoding of the time feature, we can construct an adjacency matrix between all entities and timestamps that counts how many times a timestamp is related to one entity. By building this temporal adjacency matrix, we can encode the timestamps as the feature of entities. For the relational encoder part, we directly adopt current solutions, using a graph neural network to capture the neighbor's information and a loss function to keep the training pairs close to each other. For the design of the decoder, we have found that temporal features and relational features may have different contributions to the results, so we add a weight alpha to balance the two kinds of features. This incurs the last problem, that is how to decide this alpha. To find the best alpha, we transfer our problem into a graph matching problem. The process of graph matching is to find an optimal permutation matrix between two sets of nodes that can minimize the edge distance. The experimental result shows that our method can achieve up to 10% accuracy improvement on supervised settings, and we can also perform unsupervised entity alignment that achieves higher accuracy than the previous supervised models. Thanks for watching.